the reason why we are actually going through all these things in quick succession is to essentially point out, as far as this course is concerned, that whatever we have learnt on laminar premix flames and laminar diffusion flames are actually applicable as we speak, pretty much in the context of more complicated application oriented areas, except that the situation is complicated by a lot of other things. For example, in sprays it's complicated by the spray statistics, the diameter distribution and so on. In the case of solid propellant combustion, we will see what else happens, and then we will move on to turbulent combustion also to show that the basics that we have learnt will be applicable there, and how it's complicated by the turbulence and so on. So in the case of solid propellant combustion, what we need to understand is essentially we have to look at two cases. One is homogeneous propellants, and the other one is heterogeneous propellants. The term propellant actually means that both the fuel and oxidizer are actually available in solid form together, and the question basically is to what is the level to which they are really mixed together. So in the case of homogeneous propellants, they are actually mixed up to the molecular level. So fuel and oxidizer mixed at molecular level here. That means when you now have a source of heat that ignites it, and then the combustion keeps going under steady state conditions, essentially what happens is the solid gets heated up and it is thermally unstable, so it decomposes into gas phase products. The gas phase products are essentially gas phase fuel molecules and oxidizer molecules, which then in turn break down further to react in a gas phase flame, and the gas phase flame releases a lot of heat that goes back to giving rise to the condensed phase decomposition products of fuel and oxidizer molecules in the gas phase. So that's how it happens. As a matter of fact, when we're looking at liquid droplets, there are also I mentioned monopropellant liquid droplets. Okay, so where you now can actually have a premix flame that is surrounding the monopropellant liquid droplet, and it pyrolyzes the droplet, and the droplet decomposes into gas phase fuel and oxidizer molecules that react in the gas phase flame. So a similar idea essentially prevails for homogeneous propellants. Example of this is example you can think about is the most common thing is what is called as double base. Double base propellants, it calls double base because it's actually a combination of nitroglycerine and nitrocellulose. So they are mixed together such that they actually form a mixture at the molecular level, and then they will decompose into a gas phase fuel and oxidizer. On the other hand, so obviously before we move on to heterogeneous propellants, obviously what we are looking at is essentially is this should give rise to a premixed gas phase flame, and so you can think about a premixed gas phase flame where the preheat zone now extends into the solid, alright, because the preheat zone essentially is where the heat conduction happens, and the heat conduction now happens into the solid, heats up the solid from its initial temperature up to a surface temperature that needs to be determined as part of the problem by supplying interface boundary conditions between the solid and the gas phase, and in addition to that you still have the same problem essentially of an eigenvalue problem, which is you have to find out the burning rate of the solid, or what is the rate at which the surface regresses. That's essentially similar to the way we did the gas phase flame one-dimensional flame structure associated analysis. In the case of heterogeneous propellants, essentially the fuel and oxidizer are mixed at a particulate level. That means you typically have, this is very typical, it doesn't have to be exactly followed this way, but typically we have a solid oxidizer powder, which means like it's typically a salt, chemical salt, and the most typical one that we use is what's called as ammonium perchlorate, and so you can use these ammonium perchlorate salt. So it looks like the common salt particles, but you can come in various particle sizes, and so essentially you have these particles that are now embedded in a polymeric fuel. So this is essentially starting out with a polymer that is a highly viscous liquid into which you now mix things, and then you set this polymer to become a solid. And so the fuel is essentially a polymer that also acts as a binder that binds the particles. And you can also of course throw in metal particles to act as further fuel to this entire mixture, but the metal combustion actually happens outside of the combustion between the fuel and oxidizer. Alright. So effectively the binder and the oxidizer. So effectively what we are looking for is the combustion that propagates the flame into the solid, that is caused by a flame that's between the fuel and oxidizer. So this is going to actually look like, now have a lot of solid particles. So typically these are like about 200 microns to 300 microns in size. The finer ones could be as fine as even 5 microns or even 1 micron in very extreme cases, but typically it's of the order of about 50 to 70 microns, 80 microns, maybe at the most 100 microns and so on. So essentially you try to have a very tight pack of a lot of large solid particles, and then you now try to pack further in between the crevices formed in between these big solid particles with further smaller particles. And so now you get these particles, and then you now have a binder that's binding the whole thing together. So microscopically, when you now have a flame that is trying to eat into this, it is obviously not going to be a premix flame, right? So even at the microscopic level, what happens is, let us suppose that we can hypothetically say we just cut it with a surface like this, and we now say that is now the burning surface. Obviously the burning surface is not going to be as flat as what it is, and we will try to see what happens, how the non-planarity develops as we speak. But let us suppose that this is what we want to think about, and now you have like an exposed area of oxidizer that is giving rise to oxidizer vapor, and there is exposed area of binder that is giving rise to binder. So this is actually let us say fuel here, oxidizer here, fuel here, and this is, if you now look at it like this, within this region, that is sort of like the inverse of the Burke-Schumann problem. The Burke-Schumann problem is where we now had a fuel in the core and oxidizer on the sides, but if you didn't really care about exactly what chemicals that are being used, we are essentially looking at two different constituents, reactant species that are coming out in this fashion. So we expect to actually have a diffusion flame over here that's associated with this. Recall we had talked about flux boundary conditions, so we can deliberately talk about where exactly the stoichiometric surface is going to attach. Is it going to be at the contact between the oxidizer and fuel or away? These kinds of issues remain to be discussed in these problems. But we also talked, when we talked about diffusion flames, we talked about finite chemistry effects, particularly near the leading edge, and then we found that we need to have something like a leading edge flame or a triple flame structure, and that is pretty much expected in these propellants, because it turns out that the oxidizer actually is a monopropellant by itself. It can burn by itself, but we need the binder to hold the oxidizer particles together and push it closer to a stoichiometric situation. Therefore you're essentially having a oxidizer rich reactive mixture, and in fact it can also go through a self deflagration. So you do have a self deflagration flame of the oxidizer very close to the oxidizer particle, out of which you now get oxidizer rich products of this flame, which now mix with the binder fuel gaseous species. And then obviously, since you now have a oxidizer rich species, you are now going to have more like a triple flame rather than a diffusion flame that extends all the way. So typically modelers have identified that you now have like a monopropellant flame for the ammonium perchlorate, then you have what is called as a primary flame in the diffusion flame that is coming from the triple flame kind of idea there, the corners, and then the trailing diffusion flame. So a typical idea of multiple flames prevails for what is called as composite propellants. Heterogeneous propellants are also generally termed as composite propellants because it is the composite of particulates in a binder, similar to composite materials and structures. And the popular idea is you have essentially multiple flames of different structure that prevails on top. And of course, as I said, you also have aluminum metal particles that are embedded. Aluminum is thermally very stable, therefore as it comes out, it's going to accumulate on the burning surface because it is just barely getting melted there at that time. It is not ready to actually get evaporated. So so as it gets accumulated, it now forms a sintered web, and it's getting heated up by this gas phase flame complex, and ultimately it now reaches an ignition temperature by which it gets ignited, and then a sintered web actually rolls out and then goes up and then starts burning as a bigger agglomerate than the individual particles that we originally had. So that's a complex problem that has a lot of ramifications in solid rocket performance where these kinds of propellants are used. So all I want to point out is we have discussed many of these issues in trying to do laminar flames earlier on, and all these ideas actually remain here as well. So we now want to also do a similar kind of overview of turbulent combustion, and to say that we want to just give an overview of turbulent combustion is extremely unfair, because it is a subject that has actually spawned a huge amount of literature. A lot of scientists have been working, and turbulent combustion is one of the things that that has funded a lot of combustion research, if you will, in the last many decades. That is primarily because most of practical combustion, barring let's say some of these things that we talk about, which are happening in very microscopic scales so that the Reynolds numbers are so small, except for this, most of the other kinds of combustion situations are turbulent in nature, right? So we are looking at, let's say, gas turbine combustors or liquid rocket combustors or furnaces or boilers and so on. Many of these things, you're actually, wherever you're going through, most combustion situations, you have turbulent flow. So effectively what you have to do is, here again, just like how we did sprays, first we have to get a hang of turbulent flows before we can actually get into the combustion. So when we did sprays, you remember, we had to first talk about spray statistics. How do you characterize sprays? How do you describe sprays? And then we will worry about the combustion. So similarly, we have to actually go back a little bit and then get a quick overview of what is turbulent about turbulent combustion, right? So that means we have to look at what is turbulence in general. We will try to restrict what we are trying to do here to the context of turbulent jet flames. And when I say turbulent jet flames, I will talk about both premix flames and non-premix flames, and let's see what that means. So when we say turbulent jet flames, so consider turbulent jet flames is what we want to do. This is very generic, because what you can think about essentially is, if you now have a little nozzle from which you now have a gas that's coming out at turbulent speeds, and you know, you use out like a jet, right? So, and then you have a lot of eddies here and there and so on. It's a caricature that I don't want to really elaborate too much. So so you now have a large turbulent jet. So you can think about this as like coming out of a burner that is fitted to a combustor or a furnace and so on. So this is a very practical situation that you come across in many applications. When you now say turbulent premix flames, you could now think about a reactant mixture that is coming out of here and then letting in air from the sides entrain into the jet. So, or if you want to think about a turbulent non-premix flame, you could now say I have only fuel coming through this, it's entraining air around, and then you now have a flame. So either way, so depending upon how that's going to happen, right? So if you now have a premixed reactants, you're now going to have a highly wrinkled a premix flame that is going to burn and consume all the reactants within a very short distance. And once again recall, so or if you now have or if you now have only fuel, right, you're now going to have a diffusion flame. The picture that I'm drawing there is essentially something like the stoichiometric surface. So what you're essentially, just like how we did the Berg-Schumann problem, if it's possible for you to actually now mark the mixed diffraction corresponding to the contour corresponding to the stoichiometric mixed diffraction, right, you now get a turbulent flame. And what is turbulent about it? Because you now have fluctuations that keep happening. The next snapshot that you try to go through, you're now not going to exactly follow the same contour. This is an instantaneous picture. So the next one is going to be slightly different, and the third one is going to be slightly different. Then you keep on taking these snapshots and then put on top of each other. You now get lots of these kinds of curves which you now kind of form a band, and that is what you would call as a turbulent flame brush. Okay, so it essentially causes a brush-like structure on an ensemble averaged manner. Similarly, for the premix flame, again, let's go back and think about what happens in a laminar situation. We talked very significantly about the Bunsen burner experiment, where you could now have the hole at the bottom that allows for the air entrainment open and set up a premix flame, and then start closing the hole very gradually, and then convert this premix flame into a diffusion flame. And we now find that the diffusion flame is a lot taller when compared to the premix flame. Right, a very similar situation would exist for turbulent flames as well, simply because in the case of diffusion flames, the combustion is actually diffusion controlled, so the heat release is not going to be as intense, or the chemical reactions are not going to be as intense, because they are waiting for the mixing to happen, right. Whereas in the premix flame you don't have that kind of a constraint, so the heat release is kinetically controlled, and so you now have a lot of heat release that happens within a very short region. So the volumetric heating load that you come out with a premix flame is a lot higher when compared to that of a diffusion flame. For this reason, for the same kind of thermal loading, that means the amount of fuel that you're trying to burn at a particular rate, your premix flames are typically very compact when compared to diffusion flames. This is true as well in laminar as in turbulent flows. So if you're now thinking, if you want to think about how, so just like how I said, you can now look at the stoichiometric surface for the diffusion flame. I also meant to point out, you could now think about a local turbulent flame speed that is trying to match the flow and then trying to set itself up, right. And there we have a little problem. Am I going to actually say this instantaneous flame is the one that is traveling at a turbulent flame speed, or is it like a turbulent premix flame brush that is traveling at a turbulent flame speed? So that the notion of what's a turbulent flame speed is a little bit difficult to think about, and we will have to talk about it a little bit in greater detail shortly maybe. The first thing that I'm hinting is, first of all, if you're completely ignorant, we will now have to talk about something called a turbulent flame speed as opposed to a laminar flame speed. We got a hint of it the moment we actually used SL, where L is a subscript indicating laminar, and I pointed out that when we think about turbulent flames we will have to alter that, and so we will discuss this. The point again I'm trying to make is the ideas that we had, like the flame speed balances the flow, the normal component of the flow, those ideas will remain. Okay, that is not going to change. So if you want to now think about all these things, the first thing that we have to do is forget about the flames for a moment. We will now look at only the term turbulent jet, right. So for the sake of looking at the turbulent jet, let's not worry about whether this is premix reactants or a fuel. We will simply say it's just a jet of some gas, right, maybe air itself, and in an quiescent air ambience. That means you're essentially looking at a jet, and in the jet you now have a region that is like where you have an unsteady shear layer, where you now have two mixing layers. We are talking about momentum mixing as well as species mixing and thermal mixing if it is not isothermal. So all these things are happening within this region in an unsteady manner. You could hope to actually view this part as essentially an unsteady laminar case if you're trying to resolve these scales in your computation or whatever it is, but pretty quickly you're now going to get into a region where you transition to turbulence, right, and then beyond this point you now have a fully developed turbulent jet. When you're now having a fully developed turbulent jet, we are now looking at a lot of eddies over here, which are primarily homogeneous isotropic. So we are looking at situation where if you now pick a point which is given by x and another point which is given by x plus r, distant r apart, then we now characterize this by having a cross correlation between the two. Now if you're now looking at this region where it is fully developed turbulence for homogeneous isotropic turbulence, the location x doesn't matter. Location x is arbitrary, and all you're looking at is essentially the actual distance rather than the displacement. So that means you don't have to look at this in a vector form. So the direction didn't matter because it's isotropic. So the location didn't matter because it's homogeneous. Therefore, r can be replaced by mod r, which was, let's say, simply r without the vector, and then what you're looking for is a velocity correlation. So the starting point of thinking about turbulent flows is to think about a velocity correlation here, that is a spatial correlation. That means you're essentially looking at turbulent fluctuation at x comma t correlated with the turbulent fluctuation at x plus r comma t as an average, right? And then then you normalize this. So the normalized correlation f of r comma t then is just take the correlation r and divided by the RMS, so u prime squared t the whole bar. And so why are we bothered about this? Because we want to now step into how this looks like. So if you now look at how the f of r comma t looks like, then it's going to be versus r, let's say. So how does it look like versus r? It typically goes, it's normalized, so we don't have to worry about the magnitude. It goes asymptotically to 0 as you go further out in r, and with respect to this we could now say somewhere along here we have a length scale eta, which we would now call as the Kolmogorov length scale, and somewhere in here we would now have a length scale L, which we would call as the integral length scale. We will talk about these things a little bit more carefully, so let's not worry about them at the moment, trying to write down. But what I'm interested in is if I can actually have a function that approximates this to good measure, and that would be 1 minus 3/4 c over k epsilon r to the 2/3, where k, what we're talking about is k is what is called as the turbulent kinetic energy, which is equal to, for isotropic turbulence you can say this is equal to u prime 3/2 u prime squared, where u prime of course is the fluctuation over the mean of the velocity, and epsilon is the dissipation and C of course is what's called as the Kolmogorov constant. Kolmogorov constant, and then we want to talk about what is the integral length scale. Integral length scale L of t then is integral 0 to infinity f of r comma t dr, that is essentially the normalized correlation integrated over all distance, and then you now get a measure of a scale that kind of caps the lot scale structures. So and we will see what that means pretty soon, and then you now have what's called as the Kolmogorov length scale, which is the smallest length scale in your flow. Essentially what's happening is you now have a turbulent flow in which you now have a cascading that happens that goes all the way down to the Kolmogorov length scale. So eta is nu cube divided by epsilon the whole to the 1/4, where nu is the kinematic viscosity, and of course epsilon is what we call as the turbulent dissipation sometime back. All right. We will also talk about a Kolmogorov time associated with the length scale, and we will talk about these time scales and length scales and the velocity associated with these for many of these scales, but at the moment we are discussing the Kolmogorov scale. So Kolmogorov time T eta is nu over epsilon to the half, and Kolmogorov velocity Vn is nu epsilon to the 1/4, right? And between the large scale and the Kolmogorov scale, we could now think about a discrete sequence of eddies, and the reason why we are talking about these things is because ultimately we want to compare these things with a laminar flame thickness. Okay, so when you now talk about combustion, we now have length scales associated, length scales and time scales associated with the flame and the flame speed that's associated with it. So we want to be able to compare these scales with those of the flame. So we now talk about a discrete sequence of eddies. Discrete sequence of eddies within what's called as a inertial subrange. I'm going to explain this soon. With a spectrum, with the energy spectrum, but let's first, I mean it's kind of like a chicken and egg thing. So we first have to talk about the cascade and then the spectrum, or vice versa. So this is basically L divided by 2 to the n, where of course until we reach eta, where n goes as 1, 2, etc. That means for every eddy size it's half the size as the previous, the bigger eddy. Essentially that's how we keep on looking at a discrete sequence. And what we can find out when in this inertial subrange, essentially the dissipation remains constant. You have a constant dissipation mechanism that works on these eddies. Therefore we could now say that epsilon is essentially like Vn squared divided by Tn, where Vn is actually the velocity associated with the nth eddy, and Tn is the time associated with the nth eddy, and this would be the same as V eta squared by T eta, where eta and T eta are essentially the Kolmogorov scales. So then the next thing that we want to think about is what's called the wave number. For some reason the turbulence community is very fond of K, maybe because Kolmogorov, they like Kolmogorov a lot, so they keep using K for the turbulent kinetic energy as well as the wave number and so on. So this is typically like 1 over the length scale, and what we are looking for is the energy density, which is the kinetic energy density per unit wave number. Okay, so we can now think about a spectrum, right? E of k versus k, and usually we are looking at a spectrum that kind of looks like looks like this, and you can now think about a division here where you're looking at this is the large scale, this is the large scale, and this corresponds to 1 over L, which is the integral length scale, and this corresponds to 1 over eta, the Kolmogorov length scale, and we are looking at this region as the energy containing eddies or energy containing, you can say, integral scales, and this region is now referred to as the inertial subrange, where you now have a constant slope of minus 5/3, that is a famous law there, and then below the Kolmogorov length scale is the viscous subrange. So essentially what's going on is turbulent flows are of such high Reynolds numbers on the whole based on the large scale that you have a predominant inertial effect over the viscous effect as you keep on going down further and further to smaller and smaller scales until you reach the Kolmogorov scale, beyond which the viscous effects begin to be important, right? So this is how this thing pans out. So it's kind of like a 10-15 minutes of turbulence, or less than that maybe, right? Just about enough for us to think a little bit about what happens when you now throw in a flame on top of this, right? So and then what we want to do is to think about premixed turbulent combustion. Right. Now the first thing that I would like to point out as an empirical fact or an observation is when you now have a turbulent flame, it now propagates a lot faster than a laminar flame, corresponding laminar flame. How do I get there, right? How did I get to that point? Essentially what it means is now you have a lot of these eddies in the flow that are trying to wrinkle or corrugate this flame, and you now have on the whole a flame that looks thicker and wants to reach ahead of itself. So it's like a very crude way of thinking about this, and then we have to think a little bit more refined manner, but effectively it now gives rise to a larger flame speed when compared to the laminar flame. And if you now thought that the laminar flame speed under typical conditions are of the order of a few tens of centimeters per second, the turbulent flame speed or speeds are about an order magnitude more, so they actually are in the range of meters per second, right? Still quite smaller when compared to most of the flow speeds that occur in let's say a gas turbine engine. So if you now think about a gas turbine engine where you're still looking at subsonic flows, we are not talking about supersonic combustion here, maybe not in this course. We are looking at subsonic flows, highly subsonic. We went through this long ago when we wanted to show that the pressure remains more or less constant in low Mach number conditions, and we said that the Mach number is of the order of about 0.1. And since the temperatures are pretty high in the combustion zone, your speed of sound could be like of the order of 1000 meters per second for the kind of temperatures that we are looking at, and so we are looking at flow velocities are of the order of many tens of meters per second to 100 meters per second. That kind of 100, that's the kind of speeds we are talking about, as opposed to which the turbulent flame speeds are still quite low, right? And this is obviously nothing to do with detonation speeds, okay, and they are like about 3 orders magnitude apart. So you now have to think about the ideas that we had about flame shapes that are attained. Like for example, if you had like bluff body V gutters, the flame still, with the turbulent flame propagation, it still tries to align itself at an angle to the flow such that the component of the flow velocity will match this flame speed. So what you're talking about as a flame speed is this flame speed here is kind of like a time averaged flame speed. So what happens in reality without having to average, right? So for which what we want to do here is to actually look at the physics of what's going on instead of thinking about like let's say empirical correlations on how the turbulent flame speed varies relative to laminar flame speed and so on. That is for maybe a special course on turbulent combustion itself where you get quantitative about it, but here we just want to qualitatively look at the different regimes of turbulent flows, right? So the idea of turbulent flame regimes comes from several investigators in the late 80s. So the first of which is Borghi, 1985. In fact, the early researchers used to call this regime diagram as the Borghi diagram, but it's been also put forward by Peters and refined further, and Bradley and co-workers, it's like 1989. Ponsoy et al. Many of these people are still active researchers in the community, and so you can see that this is not very old. It's only about 20 years old idea. So what we want to do here is to assume a unity Schmidt number That means we don't want to make a big distinction between viscous mixing and molecular mixing. SC, which is nu over d, we'll now take this as 1, and we now go through a few definitions here. So define our flame thickness LF. Capital F refers to flame, not fuel, and we will stick to this when we are doing diffusion flames as well. Equal to d over SL, and you're using SL, you see, and that means we are actually thinking about essentially a laminar flame that is going through a fate of wrinkling and so on when it is subjected to the turbulent eddies, right? And then we want to now construct an idea of what a turbulent flame looks like from essentially what's a laminar flame, right? So we are using a laminar flame speed, and then you have a flame time, which is Tf equals d over SL squared. Let's see, order of magnitude expression that you would get there. So we want to define a turbulent Reynolds number. turbulent Reynolds number, which is defined as RE equal to, let's say, V prime L over nu, where V prime is the turbulent intensity. It's a measure of the fluctuation, right? The turbulent velocity fluctuation. It comes from how you can define your kinetic energy. That means you can say you're looking at something like this under square root. That means this is basically 2/3 K power half. Okay, so that's how the turbulent intensity comes from. And L is of course the integral length scale, and nu is the viscosity, and therefore since we are using Schmidt number equal to 1, we say this is actually V prime divided by V prime L divided by D, and we just defined the flame thickness as LF equals D over SL, so D is LF SL, so this is going to look like V prime L over SL LF. It's sort of like a velocity ratio times the length scale ratio, right? So the velocity ratio here is, we are comparing the turbulent intensity versus the flame speed. We are comparing the integral length scale of the turbulent eddies with the flame thickness, right? So I'm trying to sort of implant this idea right here because that's kind of the way we are going to think about this. The next thing that we want to think about is a turbulent Damkohler number. Damkohler number is something that we have come across earlier on, which is essentially a flow time by reaction time. So it compares your flow time scale by the reaction time scale, and so typically it's quite large because it takes a lot of time for the flow to make a significant movement, like over a characteristic length scale of the geometry, when compared to the time it takes for the reactions to happen. So Damkohler number is now defined based on this, but you'll find that it's a little bit different from the way Reynolds number turns out to be. This is essentially time scales, right? So this is actually SLL divided by V prime LF. So it's actually coming from L over V prime for the flow time divided by LF over SL for the chemical time. So it's sort of like saying this looks like this and this looks like that. They kind of look very closely similar, but they're not, right? So keep in mind, don't get confused about this. And we now have a Karlovitz number. Ka, so Damkohler number as the symbol dA, Karlovitz number has a symbol Ka, which is effectively Tf, the flame time divided by the turbulence time. So this is you can say Lf squared divided by eta squared in terms of length scales, or you can say Vn squared or V eta squared, V eta squared divided by SL squared, whichever way you want to say. This is essentially, in all these cases we are looking at basically ratio of flame scales to Kolmogorov scale. Flame scale to flame, okay, you can say flame scales because it could be time scale, length scale, whatever, Kolmogorov scales, right? And with these we should be able to show Re equal to dA squared Ka squared. So that kind of sounds like Daka is equal to square root of Re. So that's some way by which you could remember. Now what we have been thinking about a laminar flame is pretty much the same as what we thought earlier, which means it has a preheat zone and a reaction zone, right? And then the preheat largely the flame thickness is mostly preheat zone. For typically a high Damkohler number or a high activation energy situation, your reaction zone thickness is quite small when compared to the flame thickness itself, and it's given by what's called as the Zeldovich number, right, or the Zeldovich scaling. So you can scale the flame thickness by the Zeldovich number in order to get the reaction zone thickness. We have done this earlier when we were talking about laminar flames. So we can now form a second Korolowitz number based on the reaction zone thickness alone. The reason why we are thinking about this is, first of all, recall we were talking about these things as well as the turbulence length scales, because we want to now begin to compare how the turbulent length scales are going to be relative to the flame thickness, right? And what you are thinking about is, and you now keep on changing your regime, you are now going to have a situation where the turbulent length scales are typically much larger when compared to the flame thickness, but as you now keep on changing the regime, you now get into a situation where the turbulent scales are going to be small enough to be able to enter into the preheat zone but not the reaction zone, right? And then ultimately can we get it to be even smaller than the reaction zone, and so on. So this is how we want to go through. So therefore we also want to keep a track of the reaction zone thickness alone rather than just the flame thickness on the whole. So for reaction zone thickness, L delta in the premix flame, a second Korolowitz number Ka subscript delta can be defined as L delta squared divided by eta. We are still comparing this with the Kolmogorov length scale, and of course we can show that this is equal to delta squared Ka, where delta squared is essentially the Zeldovich scaling coming between the flame length and the flame thickness and the reaction zone thickness L delta. We will just stop today with showing, or this is probably a good time to stop. I think we finish these definitions. We'll pick up from here tomorrow.